A group project, we choose the topic that is robot maze navigation system that use search algo to help the robot move from the starting point to the goal. The robot must identify a suitable path, avoid dead end, and reach the destination using effective search strategy. Therefore, we compare four algo, and then this is our group member, um, Christopher Wong Teck Hao, and then me is Kong Ling Ji, then Kong Yung Han, and our last member is Amira Aisha.
For this project, a robot must navigate through a warehouse maze to find a valid path from start to goal. It must avoid obstacles like blocked cells and shelves. The robot can only move up, down, left, and right. And we use four algorithms, which are BFS and DFS, that are uninformed search, and greedy best first, and a search algorithm that are informed search. For the problem description, the robot must find a path from start at position which is 5, 0. To goal at position 0 sits in a 6 by 7 maze. The robot can only move up, down, left, and right. Each step costs 1. It can only move through empty cells, the start, and the goal. It cannot enter block cells X or shelf hashtag. For the search problem formulation, we have 5 elements. First, the initial state is at position 5, 0, where the robot starts. Second, the goal state is at position 0, 6, where the robot needs to reach. Third, the state representation uses row and column coordinates. Fourth, the actions are moving up, down, left, and right. And lastly, the path cost is 1 for each step. For example, a valid path from start to goal requires 11 steps. And for the goal implementation, our goal is to implement 4 search algorithms to solve robot maze navigation and compare their performance. The algorithms are divided into 2 types. Uninformed search includes BFS and DFS. Informed search includes greedy best first and a search algorithm. We will compare them based on 4 criteria, which are path optimality, nodes expanded, time taken, and memory usage.
Okay, now is the algorithm implementation part. So in our case, we will use the four algorithm that we use is the first search, the previous search algorithm designed using the linked list, and the deep first search using the last in and first out. And next for the greedy best first, the Sn equal to Hn, where Hn is estimated distance from the current node to a goal, and the A star search algorithm consider both the actual path, cost, and the heuristic value. It is derivation function is the Fn equal to Gn plus Hn. And now is the algorithm in the demonstrate. So now we are using the Java to demonstrate the algorithm. So the first, this is the node for our node class for our project. That is the used to declare the heuristic function and the path cost function. And next for the maze environment class, that the situation of the maze that we using the empty to define as a 0, and the obstacle or the self defined as a 1, and the goal state is defined as 2. So we got a 6 row and a 7 column for our maze. And we also got to define the how the movement of the robot, so up, down, and left and right. And next for the search algorithm class, that this class is put all the algorithm function that used to calculate the root. So first is the BFS, and then the DFS, and the greedy search. Last is A star. So, and then this is the main class to run the whole file. So let's run it. Okay. Now the run is finished, so we can see that the BFS have the node expanded like 31 and DFS at 28 and greedy 16 and the A star is 21. So the path length they took is the 11 and DFS 13 and the greedy and the A star are same, that is 11. However, the time that taken, the BFS is the longest, almost the 4 second, and the DFS used the 0.6 second. Greedy used the 3 second, and the A star using a 0.3 second for run all the program. So the memory they took is 450 for the BFS. DFS using the 163 and the greedy best first using 47 and the A star using a 36 for this all algorithm for the maze. So that's all for me.
Heuristic design is a heuristic function estimates the distance or cost from the current state to the goal state. Hence, greedy best first search in a search algorithm decide which node should be explored first. Is the informed search algorithms can reduce unnecessary explorations and move more efficiently the goals. 5.1 Manhattan's distance heuristics. Manhattan distance calculates the estimated distance between the current positions and the goal positions by adding the difference between their row values and column values. So the formula is Hn equal to current row minus goal rows plus current columns minus goal columns. For example, if the current position is 2, 4 and the goal position is 6, 6, the heuristic value is called as Hn equal to 2 minus 6 plus 4 minus 6 equal to 4 plus 2 equal to 6. So the derivatives of the heuristics, the robots move in a grid and can only move up, down, left or right. Helps improve search performance by guiding the robot towards the goal. As a result, informed search algorithms usually expand fewer nodes than uninformed search algorithms. 5.3 Admissibilities and consistencies covers the minimum possible numbers of moves needed to reach the goals considering obstacles. Since obstacles can only make the actual path longer, Manhattan's distance will never be greater than the real path cost. The heuristic satisfies the consistency conditions. Because Manhattan's distance is both administrative and consistent, it is suitable for S search algorithms. This allows us to find an optimal path while reducing unnecessary node expansions. Then I will pass the baton to the next presenters to present the 6.0.
Next, I will explain the comparison and performance measurement of each search algo. In this project, we evaluate the algo using time complexity and also space complexity. Time complexity shows how long a algo may take, while space complexity shows how much memory it may use. A robot, it can move in four directions with its up, down, left, and right. Therefore, the maximum branching factor in this project is 4. Next, let's look at um, compare the complexity of BFF, DFF, greedy best first search, and A star search. So BFS explore nodes level by level, so it can guarantee the shorter path, but it usually use more memory. And then DFF explore the deeply first, so it may use less memory, but it may not find the best path. Greedy best first use a heuristic to move closer to the goal, but it can sometimes choose the wrong way. Meanwhile, A star combine the actual path and also heuristic cost, which help to balance the efficiency and then accuracy. Okay, next is the performance comparison result. Based on the result, A-star search performed the best overall. It found the optimum path length of 11, also record the faster execution time, 0.3 millisecond, and use the lowest memory, which is 36 KB only. Although greedy best first expand the fewest node, but A-star is more reliable because it still produce on optimum solution. And also BFF found the shorter path, but it used more memory. Okay, next is our optimization technique. To improve the search process, this project used a visited set, also known as memoization. A visited store location that has already been explored. This prevents the robot from revisiting the same cell again and again. Because of this, the algo can reduce the repeated exploration, avoid unnecessary movement, and prevent the infinite loop. Overall, the search become more efficiency and also organized. Next is our discussion and conclusion. In conclusion, this project compare 4 algo for robot maze navigation. The results show that A-star is the most suitable algo. It gives the shorter path, the faster execution time, and lowest memory usage. This is because A-star consider both actual path cost, that's GN, and also the estimated distance to the goal, HN. Therefore, A-star provide the best overall performance for this maze navigation problem. That's all from us. Thank you.